Find the ratio of the potential differences that must be applied across the parallel and the series combination of two capacitors C1 and C2 and their capacitances in the ratio 1 is to 3, so that the energy stored in the two cases becomes the same. So we need to find the potential ratios from the given problem. I understood that two capacitance are there, that is C1 and C2. So their capacitance ratio C1 upon C2 equal to 1 over 3. And these two capacitance are connected in series. So capacitor C1 is connected to C2 to a potential source. So that is Vs in series. And same capacitors, they connected in parallel to a potential source, that is, I can take that potential in the parallel, the same capacitors C1 and C2. So what we need to find? We need to find the ratio of the series to the ratio of the parallel of the potential differences. So this we need to find it out. And the given that, very important that, it is that in the two cases the energy stored of the two cases becomes same, means the energy stored in series equal to energy stored in parallel. So this is the key equation to go forward. Suppose if I write the energy stored expression, what is the potential energy expression? That is equal to half CV square. If it is in a parallel, I can put that capacity in the parallel, potential in the parallel, energy stored in the series, which is equal to half CV square, that is capacitance in the series. So this is capacitance in the series and potential in the series. Therefore, since potential energy stored in the parallel equal to potential energy stored in the series, just make it equal that too. So if we can make it equal, half Cp, suppose to Cp, half Cp and Vp square equal to half Cs and Vs square. Now we cut the like terms, so half of gets cancelled. If you can separately write capacitance in the parallel upon capacitance in the series, which is equal to potential in the series square upon potential in the parallel square. Now this is my final task. If two capacitors are in parallel, what is their total combination? The total combination when they are in the parallel. So that is C1 plus C2. Since Cp equal to C1 plus C2 and C series equal to 1 over C1 plus 1 over C2, which equal to C1 plus C2 upon C1 C2, that is 1 over C. This is 1 over C. If we can write that Cs series in the series, it will become C1 C2 upon C1 plus C2. So if we can take that expression set here, therefore C1 plus C2 upon C1 C2 by C1 plus C2, which equal to V series square upon V parallel square. Okay. Now let us do simplification. Now if you can send this denominator to numerator, that will become C1 plus C2 whole square upon C1 C2, which equal to V series square upon V parallel square. Let me simplify it here. For the simplification, since I know the value of C1 upon C2 equal to 1 over 3, the ratios of the capacitance. Now I would like to convert this expression in terms of C1 by C2. For that, I will divide the equation C1 by C2 whole square on the numerator and the denominator with C2 square upon C1 C2 upon C2 square. I am dividing on the both numerator and denominator with C2 square, because to get that value into the known terms, that equal to Vs square upon Vp square. Now for the simplification, the numerator I can write like this: C1 plus C2 upon C2 whole square, since they both are having the square term, and the denominator I can get that C1 C2 upon C2 square. Now you can cut one term at here and you can write the rest of the terms, which equal to Vs square upon Vp square. Now let me take this space, need not to go down. Now in the numerator also I can do the same. So I can divide with the C2, that will be changes as C1 upon C2 plus 1 whole square. Upon in the denominator I can get that C1 by C2, which equal to Vs square upon Vp square. And we know that the ratio of the C1 by C2 value goes to 1 over 3. You can substitute that value 1 over 3. 1 over 3 plus upon 1 over 3, here is supposed to whole square, which equal to Vs square upon Vp square. Now in the numerator, do the LCM. 4 by 3, it means 16 by 9, including the square, upon 1 over 3, which equal to Vs square upon Vp square. Now let's simplify it here. Now you can reciprocal it there. 16 by 9 and do the reciprocal, that becomes 3 by 1, which equal to Vs square upon Vp square. And 3 in 9 3 times, so 16 upon 3 equal to, I will take under root everything, which equal to Vs upon Vp. So split the root, it will becomes root 16 upon root 3, which equal to Vs by Vp. Therefore Vs by Vp, the ratio of the potential to series to parallel, equal to 4 by root 3. Yeah, 4 upon root 3. So if the capacitance are connected in series and the parallel, their potential energies are equal. And what is the ratios of the capacitance to the series to parallel? Vs by Vp, I hope I got the same. Yeah, Vs by Vp, which equal to, this ratios is equal to 4 upon root 3. So this is the final answer we need to get. Here we need to make it equal. The potential energies of the two combinations, series combination and the parallel combinations, is equal. Yeah, usually that happens when we connected in series or parallel, the total potential energy remains constant because of the conservation. But something happens in the parallel combination, energy gets lost and charge gets conserved. That only happens in the parallel combination.